The hardest part was choosing names. Yeah. But again, the hardest part
Oh, sorry. I'm speaking now. Is that good? Can you hear me? Yes, good.
So, what did you the desire really wanted to it's not a and then you I feel like that's where you do your abstraction of your topic. You don't have to, but I have to be able to use that. You don't in the policy.
Okay, welcome back. So the midterms are graded. We're going to send them out tonight. People did actually fairly well. So like the whole class did fairly well. So yeah, you should be those should be available for you tonight, and with an explanation of the distribution and stuff like that. So today, I want to apologize just because this is actually one of my favorite topics, and I changed my mind about 15 times about how I was going to present it, and then the world has conspired to basically give me zero preparation time. So I'm going to wing it a little bit more than normal. You guys can help me by asking questions if I say something that's without the proper background. Okay, so we talked last time about trajectory optimization through contact, right? And there were a couple really important ideas that came through that helped us write the trajectory optimization problems, which turned out to be, I think, fairly natural once we had the right language. And the first part of that language was this picture that you could have in your head of hybrid systems, where we have some dynamics. We have, let's say, it's often just a function of q, but it could be a function of q. Let's say x and u in general. 0 is my guard. Then I have a reset map, which is x plus x minus. So right at the transition, there's an instantaneous transition at potentially an impact, and then I have a new dynamics over here. And there were a couple different ways that we wrote the dynamics. We talked about writing it in minimal coordinates. Where in that case, I would think of this as potentially even having a different, in this mode over here, I might even have a different number of state variables and a different dynamics, certainly, but the same control input. So for instance, for my slip model, my spring-loaded inverted pendulum, in the flight phase, it was sufficient to think about the XY position of the center of mass, and I didn't have to actually, the dynamics of the leg didn't affect my dynamics since I assumed it was massless. But over here, I had actually a different dynamics governing it. When the spring-loaded inverted pendulum was in stance, then actually the entire dynamics were governed by, I switched between R and theta last time too, but R and L, but basically the polar coordinates of the leg, and X and Y are simple to extract if you're just tracking this as your state. So I have not only a different F, but even a different state space representation. And the key was, key observation is that those coordinates are minimal in the sense that this is the smallest number of variables that can completely describe this. One of the big advantages, as we'll see, of writing the dynamics in minimal coordinates is that this becomes an unconstrained dynamical system. So I just have a standard differential equation. Okay? Contrast that with the maximal coordinates. Which, if we're going to do this hybrid trajectory optimization, I'll say this is sort of the hybrid case, then in my mode 1, I'll write the system, we talked about writing the manipulator equations with the constraint forces appearing naturally. I could write that in manipulator form, or I'll just write it in F form here. So now I have a differential equation with the contact forces, lambda. And then I have some different constraints that are telling me what lambda has to be. So this would be, for instance, just some set of equations here that describe how lambda is related to x and u. In the case of the aerial phase here, those equations are particularly simple. Lambda equals 0, right? And then I just get my original dynamics back, okay? In mode 2, or any other mode of the system, I actually have exactly the same x, exactly the same f, but I just have some different constraints that are active telling me how lambda has to behave. Okay? So I'll have G2 x u lambda equals 0. And for instance, when this thing is on the ground in stance, the constraint equations, we had a couple different ways to write them. The fundamental equation here is that somehow the foot, which is a function of q, is in some constant location. Right, so this is a 2x1 vector, in this case the xy position of the foot. That foot stays constant. That also implies some other constraints. For instance, the derivative of the foot position, which is going to be a function of q and q dot, has to be 0. The acceleration of the foot, which is going to be a function of q dot, ultimately u and lambda equals 0. And this is the one that tells me what lambda has to be. So this is the workhorse in this particular formulation. This is the case for hard contact, rigid contact, non-penetration. Sometimes in my other models, it's sometimes easier for soft contact. I have a simpler set of equations, which for instance says that lambda is just negative k foot y of q or something like this, right? Some spring law. That is also an equation of this form if I'm using a different contact model. Okay, so this is now The maximal coordinates, again, in the hybrid case, where I call out in each mode separately, I say that this is a mode defined by which contacts are active. That specifies then a set of equality constraints here. I get my dynamical system with these equality constraints. Yes?
So for modeling a system where you have a foot which has relatively small friction, so like slipping is very reasonable, would you probably do maximal coordinates first or minimal coordinates first?
So you can do either again. In minimal coordinates, you need a mode for when you're in sliding friction, in which case lambda is going to be exactly the opposite direction, right, subject to the friction. It's going to be on the edge of the friction code pointing in the opposite direction. You'll have a different mode for when you're in sticking, and that mode will be valid. The guards of when that mode stops being active and you transition to sliding are the friction cone. So we should say yes, that makes sense, and we could write that down. You should also say, I have to write that down, every possible permutation of sticking and sliding for every possible contact down, and I don't want to do that. That should be your other reaction, and it gets gross fast, okay? Which is why we end up, in practice, favoring some maximal coordinates for those kind of problems. Okay, but that's a great question. Friction mostly fits into these same pictures. I've been leaving that detail out because it just adds a lot of complexity. There is one other thing that we mentioned, right? So given those two formulations, we were able to do trajectory optimization by just writing with a mode sequence, right? So where it just implied that I'd have some amount of points in my trajectory in mode 1, and then I'd have my final condition has to be on the guard of that, and then I'd have my jump condition, and then I'd have my new ones. You could write that in the minimal coordinates, which is nice. I don't have to add any constraints, but the trajectory optimization could also eat up this, where you just have lambdas, have the additional decision variables, and at every knot point you just add extra equality constraints. Both of those approaches worked. But we also talked about one other form of maximal coordinates, a particularly sort of important one, which we called the complementarity formulation. Which is I could take these, all these constraints that are equality here, a different set of constraints that are equality here, I could summarize them all with a handful of inequality constraints. Okay, so I can write x dot equals f of x u lambda, and then I can write down my contact constraints, for instance, as inequality constraints. That's saying like my foot is always greater above or on the ground, right? I can say lambda is always pushing up, it's never pulling on the ground, my constraint forces. And then I can say that phi q times lambda equals 0, which is the complementarity constraint. You could have many contact forces, many contact conditions. They all have to be equal to 0. And this says that, the way to read this is that either phi q equals 0 or lambda I equals 0. And that's a particularly compact way to write all of those, and it's valid for all mode sequences. You have to be careful about the impacts because lambda does have is a delta function at the impact, but this is a compact way to write all of those. Okay, And so in this form, we could do trajectory optimization without a mode sequence. I would say that in some, the takeaway, if I could just give you sort of anecdotally, this is very robust, very practical. You'll get it to work. If I do trajectory optimization without a mode sequence, I'd say your mileage may vary. But you can do it by just telling the solver about these constraints. Right? You can also do it by just having lambda be described as 0 when VQ is greater than 0 and negative K VQ when VQ less than or equal to 0. This is the soft contact. But in both cases, it's summarizing those G's for all X, U, and lambdas, but it's making uglier constraints somehow that are either piecewise or inequality constraints, and they're much harder things to hand to the solver. Okay, so for the goal for today is to, again, we're going to play back and forth between minimal coordinates and maximal coordinates because they're good for different pieces. But we're going to look at the stabilization problem and the Lyapunov analysis problem through contact. Okay? And we'll get to the trajectories, but even stabilizing a fixed point is actually a surprisingly rich thing to discuss. Okay, so there's actually so much to say about the sums of squares version of this that I'm going to say it first, and I'll just say this. I'll give you the teaser for it, and we won't go into the full details of the sums of squares version. So let me do that first, because you can make sums of squares work through contact. And the way to see that, again, I'm sweeping some details under the rug, but these equations are just the same equations I had before, right? They're my MQ, Q double dot, plus CQ, Q dot. With some new contact Jacobian equations. The extent to which these are polynomial equations has not changed. If I felt like I could do sums of squares for pendula and acrobat and quadrotors, then I should be able to still do it here because J is just as polynomial as these. Now they have sines and cosines, so I have to either play my trick to have these be S equals sine theta, C equals cosine theta, and add the sine squared plus cosine squared equals 1. Or I could do a Taylor expansion of this. Both are useful in different domains. Okay? But I can write a sums of squares problem now where I could say I'd like VQ dot to be, for all x and for all lambda, VQ dot has got to be greater than or equal to 0, and it's 0 at the origin. And then I'd like to say I can restrict that now to some domain, for instance, VQ dot less than rho, if I'd like. If I didn't want to do a region of attraction, lambda is going to be greater than or equal to 0. I'll restrict it in that way. So I'll use the Lagrange multipliers to knock out these extra conditions, right? And similarly, phi of q greater than or equal to 0. These are all valid for S procedure, or Lagrange multipliers. Right? You can imagine, just like, on the midterm, for instance, I could have included terms like this, and it wouldn't have added significant complexity to the way we write down the problems. It does add significant numerical complexity. The more Lagrange multipliers you have to tack on, the worse the semi-definite programming solver cries when you ask it for an answer. But this fits into the mathematical framework. But it doesn't completely describe the solution. We still have this one to deal with. Fortunately, if phi q is polynomial, and lambda is one of my indeterminates, this complementarity constraint is actually just another polynomial constraint. So this extra constraint is also polynomial. Okay? So it can also be an S procedure. And so I can add all of my standard tricks to do sums of squares through contact. There's significant effort in showing that this is a valid approach, even with the potential, the fact that lambda can potentially be a delta function, but that work has been done. There's also some significant structure in the problem. The way you write down these functions and hand them to the solver, it turns out that in order for these inequalities to hold, they actually have to hold in the case where there are no contacts, and they have to hold if you were only to turn on each contact one at a time. So even if I'm concerned with a case where I've got multiple contacts, it turns out you can actually verify independently one contact on, another one contact on, and if all of those conditions hold independently, because of the way lambda enters these equations, we can actually certify the more complicated conditions. So this actually has a very nice set of sums of squares programs that come out, and we in practice can do Lyapunov analysis through contact. I'll show you some of the key figures here. So this is, this line here is just my v dot less than 0, written in a slightly different form. V is q dot, so this is q double dot. H is the mass matrix in this paper, but otherwise our symbols are the same. So this is J, this is the frictional terms of J, which they do include here, okay. This is Mike Pose's work. And what's surprising here is that there's no term which has all of these different, like a sum of all the permutations of contact conditions. If you can verify this term happens for each individual contact, then actually the Lyapunov conditions must also hold for all of them simultaneously. So it's a pretty efficient, well, considering how complex the dynamics are, it's a pretty efficient sums of squares program. One thing that you will find quickly if you type this in is, so although V is, we're asking V to be strictly positive, we're not asking for V dot to be strictly positive. And I mentioned that actually very early on when I was motivating. It's important if you do in the sense of Lyapunov or asymptotic or exponential. In fact, once you have friction, you very rarely get asymptotic or exponential stability. You only get stability in the sense of Lyapunov. So that's just less than or equal to 0. For instance, if my system is, if I have a biped, I guess I'm a biped, I don't need my fingers. So if I'm a biped here, and I'm trying to stabilize this point right next to me here, if I'm just shifted a little bit this way, I'm not going to slide over to the side automatically. I will stay close, but I won't actually converge asymptotically. And that's a common thing with friction. Okay, and it appears in the sums of squares program. You can't ask for that to be strictly decreasing in all directions. Okay, but you'll now recognize a rimless wheel. So, the first example in this paper was showing that the rimless wheel actually goes ding, 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 and ends up being stable, right? Modest, but important. Okay, and this is using the maximal coordinates, the floating base coordinates. Okay, writing all those constraints. And this is what the region of attraction looks like. It's a little funny, you have to get your head around it, but this is the fixed point with 2 feet on the ground. It verifies some region like this. These are lopped off with the conditions that would be in penetration. So they are held out by the S procedure. It successfully, it knows that the system's region of attraction is limited by the upright, because it'll go over to a different fixed point, and it's a little bit conservative inside that. The true region of attraction here should actually go up all the way to infinity, because if I have, is that true? Yes. So that would be, this is theta versus z. It's a slice of a high dimensional thing. So if I were to drop the rimless wheel from up here, it should still land and go here. So this is a conservative inner approximation of the region of attraction. The blue region should continue straight up the page, but fitting ellipsoids in this high dimensional space, or quadratic or polynomial functions in this high dimensional space, projecting them down, we get this. Okay? This paper actually also talks about some more complicated examples, like a perching mechanism that lands on the side lands on a wall, and asking what are the successful regions, what is that terminal set, so that if I have to come in to perch and land in some successful region where my claws are going to stick on the wall, you can pre-compute the region of attraction of that, and then design all of your perching controllers to have to land inside that region. Yes?
What's the name of this paper?
It's, I'll show you. I can say it off, I'll just put it up. I'll put it in, it's in the notes too. It's long and it's it's a hard read, but. Okay, so in general, I remain cautiously optimistic about sums of squares through contact. I think for verifying passive systems, I think it works. If you have a simple controller, for instance, a polynomial controller, and you'd like to verify it, or a linear controller, you'd like to verify it, I think it works. There's a downside though. A lot of times, we don't actually know how to make simple controllers that stabilize things through contact. And the more complicated controllers, which might be the result of solving MPC or something like this, are hard to verify with sums of squares. That's one problem. Also, we can use sums of squares to do search for control. I promised that we would talk about that soon, and we will still talk about it. This paper talks about it, for instance. But the numerics of doing control design in sums of squares for these problems turned out to be very bad. So it doesn't solve all the problems, but it's a very useful tool, and it's important to be able to think about that. Okay, so let's switch now to control design. How do we stabilize a fixed point through contact? I already showed you, for instance, when we did LQR, I showed Atlas balancing and just using LQR to stabilize the system, right? So didn't we solve it already? Well, that example was written in minimal coordinates. I put a pin joint at the toe, and then we were able to, in minimal coordinates, do LQR. That's annoying because as soon as the heel hit the ground, I would have had to solve a new set of algebraic. I would have re-derived the equations of motion with the two constraints. It's a hard thing to do. All right, so a simpler version of that would be, let's say, the compass gate balancing on a toe. You could have it upright, or you could have it balancing like this, and we did that on our physical compass gates. Okay, if I put a pin joint here, plus LQR, that just works. And you should know that it works, because if I put a pin joint here and I have my compass gate with a torque there, then actually I have exactly the acrobat, right? Okay, but in floating coordinates, what happens? So let's try to do it. So if I have my equations, x dot equals f of x u lambda plus some constraint saying the foot is equals to 0, which is foot position of q equals at the origin, let's say. Okay. Then actually I can solve this for lambda. This equation is linear in lambda, so I can actually solve for that in lambda and stick it back in here. So I can write a set of equations that look like this. Now, the dimension of x here is in x, y, theta of my center of mass, plus I've got one extra leg, so it's in R4. I can approximate that as ax plus bu in 4 dimensions. I can call LQR and what's gonna happen? I guess you can guess it's not going to work, otherwise I wouldn't have set it up like that. In what way does it not work? There's only a few things that are actually going to make our LQR code say, doesn't work. One of them is this, if the system is not controllable. Okay? This system is not controllable. And it's not just because you have too many x and only one u. I mean, you have 4x and 1 u. That's actually, it could be okay. because hidden inside here is some constraint that's being enforced, the vector field that describes this equation has some constraints on it, which means, for instance, it's asking me to, to potentially go under the ground, which we know can't happen, or pull away from the ground, which we know can't happen. In those coordinates, you haven't done anything to tell LQR that there's a constraint hiding in there, okay? As such, it fails, right? So if I were to cartoon what this is happening, imagine if I were to put even my simple acrobat up against a wall here, let's say. Right, and I draw the vector field of this. There might be a lot of things you can do with different, my vector field might have interesting dynamics in a lot of places, but somewhere in here, if this is Q1, there's a constraint. The Q1's not going any farther than this. So if I'm on this, if I'm on the wall here, U1 and U2 can only move me up and down. I can have an interesting vector field out here. It's not, this is two different coordinates, so it could be going up and down. It doesn't have to go around in a circle here. But when I'm on the wall, U1 and U2 are only going to take me up and down the wall if I'm in that mode. I could break away from that mode and move this direction. I certainly can never go this direction. But if I'm linearizing around the system that was defined in that constraint equation, then I live on this line. As such, if I'm asking to stabilize this point or something like this, you're asking a question that LQR can't possibly give you a good answer to. The vector field won't permit it, okay? And it's really roughly because you're asking, LQR, if it were to return, has to give you an answer from all possible x. And it just can't do that, okay? So there's a few things you can do. It turns out if you were to this is a constrained optimization, so typically if LQR fails because of constraints, you should start thinking in your head, what would model predictive control do? Right? If I were to write this as a linear program or a quadratic program, could I get farther? Okay? And in fact, if you were to ask about stabilizing AX plus BU only from valid x, then you could write this as a linear program. Will actually succeed from valid x configurations. Because there is a solution which will take me to the origin if I stay on that valid configuration. Yeah?
But if you're not directly on that constraint, won't linearization also avoid that discontinuity? I think you don't do LQR anywhere that's not on that constraint.
So I'm going to, the setup here is that I'm going to write the linearization on the constrained equation. So the linearization is valid on the constraint. It's correct on the constraint. And so I should expect that linearization to be good. Again, it's an approximation of the nonlinear vector field, but it should be good on this constraint and be bad away. If I were to linearize it off the constraint, then I'd expect it to be good here and then very bad once it hit that constraint. So in the case where I'm on the constraint and stay on the constraint, you'd expect it to be okay, right? There is also a way that you can do the constrained LQR, which is important. A more general way, if you don't want to solve QPs or LPs at runtime, you can do the LQR on the projected coordinates down onto the constraint, right? So if I have this setup, but I also know it doesn't affect the dynamics here, but I know additional information that I have some linearization of my constraint equations, g of x equals 0, then I can do a projection of this dynamics down into the null space of that constraint, and LQR will succeed there. Okay, so I don't know, is it helpful to, I think that the important point is that that exists, and you could imagine a projection operator that describes the null space of that constraint, because this is just a linear set of equations. It gives me a smaller a and b, which it's easy to write, but it would distract from the basic point. You should ask LQR not about the 4x4 set of equations, but about the 2x2 set of equations, right? That it actually has a chance of stabilizing. So there is this idea of equality constrained LQR, which if you have that additional piece of information, you can solve as closed form as normal. You solve a smaller Riccati equation and you project it back up into your high dimensional space. Okay, so that's two approaches now: minimal coordinates, just the original LQR; maximal coordinates, where you have to announce you have to also linearize your constraints and do the constrained LQR. But you can do LQR to stabilize a fixed point that is on a contact manifold. That works. But what's the limitation in both of those approaches? It's sort of good for, doing this. It's even not so bad for doing this. But it'll never give me, if someone were to, what's the canonical problem for stabilizing a fixed point for a humanoid is called push recovery. And it's, often done with a big pole. If you have a 400-pound humanoid, you have to be pretty far away when you're hitting it with the pole or whatever. But the humanoid sitting here, you give it a push, and it comes back. So this approach, these two approaches, where I've linearized the dynamics on a constraint manifold, are able to recover from small changes in the initial condition. But as soon as the constraint changes, I have nothing yet that we've designed that will tell me how to stabilize across contacts. It's surprising. I mean, I will tell you some of the, bleeding edge approaches to trying to do that, but we're roughly stuck there, okay? If you look at the legged robots community, if you look at the manipulation community, roughly people know how to do this, they don't know how to do this, okay? Boston Dynamics, of course, does this, right? But they do that with hand-designed controllers, heuristic controllers. As soon as you sort of have to make and break contact, our rigorous tools are pretty sparse. Okay? So this is, I think, now a place where you should all be doing research. Okay, so do you have a picture of why that's important, right? So I guess even the simpler example here that I wanted to write, imagine the rimless wheel as a problem that we'll look at. That imagine the rimless wheel trying to balance. Let me add a torque at the base, just so it's a control problem. This now looks, I can plot the vector field here, q dot. It looks like the pendulum dynamics exactly, but it's got some hard constraints at the inner leg angle. Okay, if I want to stabilize this fixed point, of course, locally, I'll do a pretty good job with LQR. But if I want to recover from bigger initial conditions, there might be trajectories which actually have to slam into the wall, which slam into the ground, and then come back. It could actually bounce off the ground and come back. This is exactly equivalent. Sometimes in papers we draw it as a pendulum that's just smacking into a wall, if that's a easier way to think about it. But if I want to stabilize the upright of the pendulum, if someone pushes me hard enough, I might have to bang into the wall in order to come back. It might even be advantageous for me to bang into the wall and come back. But if I've just linearized the system around the system, the place where there's no wall, then LQR has no chance of doing that. Okay? So how do we solve the bigger problem here? Okay? The sort of moral equivalent of linearization here, when I now have these constraints that can turn on and turn off, it's now a model predictive control problem, probably. But it's a model predictive control problem with integers. Okay, it becomes a mixed integer model predictive control problem because basically I have two different dynamics which turn on and off. And so I can write that as an optimization, but it's a harder optimization. And that's what I want to do next. Okay. So if you think about how we wrote our stabilization code before, right? We had minimize. If I wrote it in the direct method, I was minimizing x of u, some, let's say, quadratic cost. Subject to x dot equals, let's do it in continuous time. And maybe I have x0 is my current x, and maybe I have some goal I want to be there at a certain time, right? The equivalent here for contact is effectively like I have a few different linear systems. I'll leave this intact, but I have AI, I'll even write the I in the script here so it's not, okay, AIXN plus BIUN, and possibly even CI. I have a handful of different linearizations that might be in working, depending on which constraints are active. And they're active when, for instance, dix plus fiu less than or equal to 0. Okay? And so x of n plus 1 has to satisfy one of these. Which one of these is specified is turned on or off by the inequality constraints. So just like here, I'm going to say when you're in this part of the state space, you should use A1, B1, and C1. When you're on this part of the state space, or if it's a soft penetration model, then anywhere over here, I'm going to use A2. When I'm over here, I'm going to use A3. That makes sense? And that's sort of the natural equivalent of linearizing linearizing a quadrotor around a fixed point. If you want to linearize a system around contact, then what you get is actually a piecewise system, or a piecewise affine system, like this. And you can stabilize that with MPC, but it's just an uglier MPC problem. Okay? There's a couple ways to see how to write it, but roughly the big trick is to use a big M notation, or there's a handful of different ways to write it. Okay? One way to write it is, I'm going to search for x, u, lambda, my x transpose qx, okay, with xn plus 1 equals ax n plus b un plus b lambda n possibly plus c. Okay, and now here's the trick. I'm going to say, of course, lambda is greater than or equal to 0 for all n. And I'll make my equivalent g of x greater than or equal to 0 for all n. My constraint equation has to be valid. But then the way, instead of writing this, that would be hard to write. It's not a convex optimization. What I can write is, I'm going to ask lambda I n to be less than or equal to bi m, and then g xn I less than or equal to 1 minus bi big M, okay? And say that bi has to be either 0 or 1. This thing is just a big positive constant. Affectionately always called big M. Okay. B is a binary decision variable. I've got to search over them too. But I've got this extra constraint like this, saying that B, when at the solution, B can't be 0.5 or whatever, it's got to be 0 or 1. What does that do? So if B is 0, then this is saying that lambda has to actually be equal to 0, right? But G can be pretty large. When B is 1, that says this has to be 0. When B is 1, this can be large, but G has to be equal to 0. So it's like turning on and off the different constraints. It's not turning them completely off, it's turning them, it's not, you'd like to say it's just greater than or equal to 0. This is saying it's still less than some big large number, but you pick a large enough number that it's away from your constraints. Does that make sense? Then the question is, can I solve these mixed integer optimizations? It's mixed because it's got some continuous numbers and some integer. This gives me a mixed integer optimization. I've got a couple slides to help me with that. Okay, so this is just the setup here, but contact forces are discontinuous stiff, right? That's what we've been saying. They can be even set valued, okay? So the linearization doesn't capture even the local dynamics, but you can make this locally valid approximation that looks like a piecewise affine system, which says that I'm just like what I wrote here, okay? that gets naturally formulated as a mixed integer convex optimization, which looks exactly like this, okay? And I can write basically that either this dynamics constraint, I can write it the way I did here with the forces explicitly, or I can turn on this constraint or turn off this constraint in the same way using these integer variables. And it works fairly well, okay? So there's a couple different ways to set it up here, but all right, so if I have a problem like this, mixed integer convex optimization, if I'm just minimizing f of x subject to g of x, but I have some constraints saying a few of my decision variables have to be integers, okay, then what does that look like? Well, that's a non-convex optimization always. But actually, it's an important special case, right? So the worst case complexity is absolutely awful. You might have to actually check every possible permutation of b being 0 or 1 for every possible b. And that could happen. The worst case bounds are very bad, okay? But this is a special case when if f and g, ignoring the integer constraints, are convex, then you call it a mixed integer convex optimization. And what that means is if I were to just take that same optimization problem and ignore this constraint, then I have a convex optimization problem. Okay? If I just remove the integer constraint, I have a convex optimization problem. That gives me bounds on what the actual solution has to be. If I were instead to say x, well, I guess I don't actually completely remove it. I say x is either between 0 and 1, then I can solve that optimization problem. And because that gives me bounds saying that the best possible solution has to be, worse than that case, because I'm going to add more constraints back in, then it actually helps me search and figure out what x has to be. You can do branch and bound search very, very effectively. And in practice, these problems are better than the general nonlinear optimization problems, the non-convex optimization problems. There are very efficient commercial solvers, and those solvers have the property that they will always give you a globally optimal solution to some numerical tolerance, or they'll report infeasible. Okay, so it's a completely different experience to work with these types of solvers. I guess there is one other case, which is they run for too long and you get impatient and you turn it off. But what it never happens is it comes back and says infeasible and you realize it just got stuck, right? So this time if it comes back saying infeasible, then the problem is actually infeasible. These problems I am willing to run on a real robot in a competition. Nonlinear, general non-convex optimization I would not be. You have to worry about the runtime, but not the solver lying to you, okay? So in practice, in fact, we did use these kind of solvers to plan footsteps of Atlas, where the integer variables now were deciding which foot had to be in which contact sequence, or in contact place, location, over time, okay? So you can write an optimization saying the center of mass has some continuous trajectory, the foot has some continuous trajectory, but the feet have to land in exactly one of the feasible regions over time, and the search is then which foot should I put in which region at which time. And those were actually practical algorithms for online footstep planning. And we actually ran those in the competition with this is Robin, who wrote the footstep planner, and he had to watch it and make sure. But and we also had a second person watching a different screen that had a stop button and balance button if they ever saw anything going wrong. He was our safety monitor, I guess, if you will.
Did you ever have to use it?
He actually used it once when we were coming off this, and we will never know if he saved us or added 10 seconds to our time. But I think he probably saved us. Okay, so the footstep planning actually doesn't do this whole rich thing, but if you want to now stabilize more dynamics, then you can add the linear dynamics back in. Okay, let me do it with this deck here. All right, so for instance, you can linearize even the full dynamics of Atlas. This is the push recovery now example, where we'd like to push Atlas, but we want Atlas to be smart about the dynamics now of making and breaking contact. And the way we did that, we thought it was funny to put Atlas inside a box, like a mime, you know. But if you could, can you solve the push recovery case where it knows to take a step and then walk back in the simple case, but if it's actually close to the wall, it takes multiple steps, pushes hands on the wall, and then comes back, okay? We can't do that reliably for the full nonlinear dynamics, but if you linearize the dynamics of Atlas, and it turns out there's an important lesson that we'll talk about with humanoids, is that there's kind of a right way to linearize the dynamics of a humanoid, then actually you get pretty surprisingly good trajectories. This is kind of, it looks like a bracing maneuver. But it works for a bunch of different, we got a new humanoid from NASA, and we were able to just start executing exactly, we didn't change the code at all, we just said load this different robot model, and it's performing different step recoveries based on, its linearization. The feet are sliding, it's sticking, but it doesn't fall down, okay? I'd love to show you more dramatic ones, but as the angular momentum of the robot increases, the nonlinearity increases, and that's the same analogy where the linearization breaks down. Yeah? Okay. One last set of ideas here. In practice, I think the mixed integer optimization is the natural, it exposes the natural structure of the problem, mostly. There's a few inefficiencies in that. But there really is some sort of a combinatorial problem. Most of the optimization, all of the optimization we've talked about so far in class has been a smooth optimization, right? Using continuous variables. This is the first time we're trying to do optimization over discrete variables, the integer variables of contact. And I think that's fundamental. You really have, if you're going to do stabilization across contact, somehow you have to choose which contacts you're going to make and not make, and what times you're going to make them. But nobody actually likes mixed integer optimization because although it has those strong properties, it's a computational bottleneck. You wouldn't expect to be able to run it at real time. It has a lot of integer variables, which people who think about mixed integer problems realize that that's bad. Runtimes are high. Okay, we're not yet close to solving this at real-time rates, but there's actually a lot of ways to improve those, where you can write sort of smaller mixed integer problems. And there's some ways to approximate the solution that you get from the MPC with simpler functions, which I would lump that under sort of approximate explicit MPC. Okay? We're also trying to do the sums of squares kind of ideas to do the control design with sums of squares. All right, so let me just give you a quick view into that world. So MPC, this was actually a presentation I gave at the sort of the birthplace of MPC. Calling out to the rich background in hybrid MPC. People know that the performance of these solvers depends a lot on a number of things: the number of decision variables, the tightness of the convex relaxations during branch and bound, and some secret heuristics in the commercial solvers. But it turns out that we can do, we've studied the dynamics of the problems that come out of rigid body dynamics and know how to write pretty tight mixed integer formulations of these problems now. Okay? So maybe the big idea is more than I'm going to get across here, but know that we thought a lot about writing the smallest possible optimization with the smallest integer variables with the tightest relaxations in order to get the best possible performance out of our mixed integer optimization. Okay? The other idea that's really important, and we didn't talk about it much even in the linear MPC, but there is a world of mixed of model predictive control where people try to figure out if I were to solve for the model predictive control from every initial condition, what does the optimal controller look like as a function of state? Okay? It turns out it can be, even for linear systems with inequality constraints that can be solved as a QP or LP, people know a lot about this explicit solution to that. They know that, for instance, the feedback controller is piecewise affine. The cost to go function is piecewise quadratic. And they know a lot about sort of the numbers of pieces and things like this. There's strong theoretical results. The problem is nobody would there was a time when people said, this is going to be the solution. We're going to pre-compute our MPC solutions. We're going to compile them down into firmware, and then we're going to run MPC way faster. We don't do solving on real time. We don't have to solve any QPs. It turns out the number of faces in the complexity of the controller is so high that it's just cheaper to solve the QP online. Okay? But still, there's some sort of mathematical structure there. So we asked the question, can you leverage that mathematical structure to come up with a simpler function that captures the control through contact with this sort of explicit model predictive, the approximate model predictive control? And this is valuable in the sense that it's got a few good examples here. Okay, so the idea is that we're gonna basically find a place in state space where we'll solve the MIQP once. Okay, we're gonna say in this configuration I do have to touch the wall and come back, or in another configuration I didn't have to touch the wall. I'm just going to be like this. Okay, and then I'm going to say, if I were to just lock in that decision to touch the wall, what are the set of initial conditions for which touching the wall at exactly that time and coming back is a stabilizing controller? And that is a question we can ask rigorously and in a scalable way. And we come out with basically a region of attraction of this one particular controller, which reaches out and touches the wall and comes back. It's very much like the LQR trees idea. We're going to fill the space with a handful of different contact schedules that come back and sort of make some contact and then come back. And we can do sort of all the LQR trees stuff to have a guarantee that we fill the space. And it just works through approximating the inner region of a stabilizing controller through contact. Okay? So we've been playing a lot with these sort of simplified, linearized dynamics robots that make and break contact, but now have closed form controllers. The onboard computation is not a mixed integer quadratic program. It's a simpler function with trees that can make and break contact. Okay, so I don't want to just jam more things, and I'm sorry, like I said, I didn't quite have as much time as I wanted, but I'll take any questions, and we'll end a few minutes early today. Yes?
What defines model predictive control?
Say it again?
What defines model predictive control?
It's a funny name. It means, it's pretty much any model-based control you could think of is a model predictive control in some sense. It is typically used for the class of problems where you're solving a small optimization or potentially big optimization at runtime. So it's planning for a short horizon, for n steps, and then you execute the first step of that plan. You let the world move you forward, and now you plan again for the next n steps, and you sort of do this as a model predictive control. Yeah?
Is any of this implemented in PyDrake yet?
A lot of it is. Some of it is actually in PyDrake master. A lot of it is in separate repos that are using PyDrake, just like your problem, like your final projects will do. So we've been pushing more and more of it up. For the relevance of your project, just ask, and I can tell you which pieces are there, which pieces are not there. The pieces that are not there are mostly due to the limitations in contact geometry normals, but those are getting resolved. Yeah?
What's the advantage of long horizon over short horizon? We are in receding control, we only take like first point, right?
So actually, even at the time of the DARPA challenge, people basically did one-step MPC because that turns out to be an easy problem. You don't have to do any integer variables. You can just look at where I am right now and solve a quadratic program always and make the decision. So that's the extreme where the horizon is 1. And it's very limiting because it can't say, for instance, if it takes me time to go over and find the wall and push off and come back, then it will never find that solution. It doesn't have, it's how far are you willing to look ahead in order to find a stabilizing solution, right? The farther you can look ahead, the more opportunity you have for the MPC to find a non-trivial solution to stabilizing. Yeah? Any other questions? Okay. I will see you on Thursday. And we will send out midterm emails tonight.
You're up meeting at 4, and then after that,
Yeah.
Sir, actually I'm exactly doing the same thing. In model predictive control, it's mixed integer quadratic programming. It's for inverter. And so